Okay, okay, last week we stopped at relative extrema and graphing polynomial. Okay, before this, I mean last week, we have learned that we will have f prime of x is equal to 0 at its minimum or maximum. So it means that if this is the graph of f, so let's say this is the graph of fx, okay, f prime of x will be 0 here, okay, at its maximum. It will be 0 over here as well. So for this one, f prime of x will be equal to 0. It will be 0 over here as well. Here 0. This one 0 as well. Here 0. This one 0. This is 0 as well. This is 0. This is 0. This one 0. Okay. So for all when it reaches its optimum values, optimum means either maximum or minimum, f prime of x will be 0. Okay, so that is something that you should know. It is not only for the highest values, but it's also for the relative minimum or relative maximum. When I say relative, it means that this is for local minimum. So it means that amongst its neighborhood, this is the lowest. It is the minimum amongst its neighborhood. Neighborhood, it might be, you might just consider this part only. Okay? But for the highest mountain over here, this is the global. Okay? Global maximum. Okay? And for this one, for the lowest point here, this is called global minimum. So it means that for all the values of x, the f reach the minimum value here. Okay, but we still have several values when f prime of x is equal to 0. Okay, it will be 0 whenever it is either local minimum, local maximum, or global minimum or global maximum. Okay, so the local minimum is called relative minimum. When we say relative, it means that it's just amongst this neighborhood. Okay, so let's say this one, relative maximum. So it means that amongst this neighborhood, this point here is the maximum. Okay, we don't compare with the highest mountain, no. Okay, we just compare with its relative or its neighborhood only. Okay, so that is the definition for the relative maximum or relative minimum. Okay, and then let's look at example 1 here. We can see from figure 4.22 that f of x equal to x squared has a relative minima at x equal to 0 but no relative maxima. Okay, so for the graph of y equal to x squared, the graph is quadratic. It's like this. Okay, if you look at the graph, so this is y equal to x squared, or fx equal to x squared. Okay, so this is the graph of x. This is x and this is the y. Okay, if you look at here, there's only one minimum point. Okay, so this is the point, right? And this is the only minimum point, and it's also a local or relative minimum. Okay, relative minimum, local or also called relative minimum, as well as global minimum. Okay, because it's the only point. Okay, But then, if you look at the graph, there is no maximum points. Okay, the graph can continues up to infinity. It can go up to plus infinity. So there is no maximum point. Okay, so we say that fx equal to x squared has a relative minimum as well as global minimum at x equal to 0, but no relative maxima. Okay, so this is if you know the graph of y equal to x squared. If you don't, it's so easy because relative minima normally will happens when f prime of x is equal to 0, right? So you just have to differentiate y equal to x squared, then your y prime is equal to 2x. You let this equal to 0 because it will be the critical point when it reach its minimum point. So what will be the value of x when 2x equal to 0? So obviously when x is equal to 0, right? Okay, and then once you know that x equal to 0, like what we did last week, we divide into two interval. Okay, I think I need to find the one notes. Okay, so y is equal to x squared, and then you have y prime equal to 2x. If you let this equal to 0, then obviously you will have x equal to 0. So this is called a critical point. Okay, critical points is when y prime equal to 0 or when f is not defined. F is not defined. Can also happens when f is not defined. Okay, so but for this case there's only one critical point, which is x equal to 0. So for a polynomial like y equal to x squared is so easy. We don't have to consider this one. Okay, because we know that for a polynomial it's always continuous. It's always continuous because this is polynomial. Okay, because it's always defined. Okay, so there is no point for y is not defined. Okay, sorry, this one. Is it f or y prime? Let me check. Critical points. F is not differentiable. F prime is not defined. Horizontal point. Okay, so it means that this one is f prime. When f prime is not defined. Okay, okay, but here it is a polynomial, so it doesn't matter. Okay, and then we want to divide into two intervals. Okay, so there's one critical point, so x is less than 0, and another one is x greater than 0. Okay, and then we would like to know the sign of f prime, right? So for x less than 0, the sign of f prime will be what? Will be negative. Okay, it will be negative, and for this one it will be positive. Okay, so it means that for the behavior of f, this one will be decreasing. Okay, and this is increasing. So if you have like this, decreasing first and then increasing, it means that it is a minimum point, right? It is a minimum point. But if the behavior is like increasing first and then it is decreasing, then this critical points will be maximum points. But for x equal to 0, it is a minimum points because it's first decreasing and then it's increasing. Okay, so y equal to 0, sorry, x equal to 0, okay, and the coordinate when x equal to 0 is y equal to 0. So this is the coordinates. 0, 0 is the minimum point. Okay, minimum points based on this table. Okay, so that's it. And then we have y equal to x cubed has no relative extrema. Okay, has no relative extrema. So for y equal to x cubed, so for y equal to x cubed, the graph will look something like this. Okay, it has a inflection point here. It has an inflection point here. Okay, but we have to determine this point is a reflection point. If we differentiate y equal to x squared, x cubed, we will have y prime equal to 3x squared, and if we let this equal to 0, we will have x equal to 0. At first, we might thought that x equal to 0 might be a minimum or maximum values. Okay, but we have to check. Okay, like before, you make the table form x less than 0 and x greater than 0. Okay, so for f prime, the sign of f prime, okay, this one will be positive. This is positive, this one is positive. Okay, and if you look at the graph as well, this is increasing and this is increasing. So there is no way that x equal to 0 is a minimum or maximum values, right? So there is no minimum and there is no maximum for this function y equal to x cubed. Okay, so y equal to x cubed has no relative extrema. Extrema means either minimum or maximum. Okay. Okay, and then x cubed minus 3x plus 3 has a relative maximum at x equal to -1 and a relative minimum at x equal to 1. X cubed minus 3x plus x. So fx equal to x cubed minus 3x plus 3, right? Is it? Okay, correct. So for this, you first differentiate. Okay? You differentiate, you get 3x squared minus 3. Okay, you let this equal to 0, and then you factorize. X squared minus 1 equal to 0. It gives you what? It gives you x squared equal to 1 and x equal to 1 and -1. Okay? It means that there is two critical points. Okay? And then you make the table form. So x is from -infinity up to -1. X is from -1 up to 1. Okay, and then x is from 1 up to infinity. So these are the three intervals that you might want to consider. Okay. Okay, and then please check the sign. So this is interval. Sign of f prime. Okay, can you please check for me? What about this one? Is it negative? Is it positive?
Positive value.
The positive, and this one?
Negative value.
Negative. What about this one?
Positive.
Okay, this is positive. So for the behavior, this is increasing, this is decreasing, and this is increasing. So if you have x equal to -1, the before points x equal to -1, the behavior is increasing and then it's decreasing. Okay, so it's like this. Okay, this is x equal to -1. It's in the middle. So it means that this is what? This is a maximum, relative maximum values. Okay, okay, and for this one, x equal to 1, it's decreasing first and then it's increasing. So x equal to 1 will be a relative minimum. Okay, this one will be relative minimum. So that's why the answer is it has relative maximum at x equal to -1 and relative minimum at x equal to 1. Okay. What about the fourth one? Okay, I think you can do it at home. It's just the same. You just have to differentiate and then you determine its interval, and from the table you see what's the behavior of the f prime, f, the sign of f prime, and then after that you go for the behavior of f, and from there you decide that the critical points is it a relative minimum or is it a relative maximum, or just a or just inflection point. Inflection points is like for y equal to x cubed. Okay, we have x equal to 0 as the critical point, but from the behavior we see that it's always increasing. It's increasing before and it's also increasing after. Okay, so it means that it is inflection point. Okay, you can determine or you can validate that it's really an inflection point through the second derivative test. But for now, we stop at first derivative test. Okay. Okay. Next, it says here the point x1, x2 here, x3, x4, and x5 are critical points. Okay, of these, x1, x2, x5 are stationary points. x1, x2, and x5 are the stationary points. Okay, so for this one, this is points where the function f failed to be differentiable, and this one as well. Okay, if a function f failed to be differentiable at a corner point, so it happens here that f prime is not defined because this is a corner point. If you look at the graph, this is a corner point. Okay, it's like a corner. It's like this one. You cannot find its tangent. Its tangent line. You cannot draw the tangent line for this kind of graph. So this is for the corner points. So okay, and that's it. Example 2, find all critical points of f equal to x cubed minus 3x plus 1. Find all critical points. So this is a polynomial. Okay, for the polynomial, the critical points might happens when f prime is equal to 0 only, because it's always continuous. You don't have to be um, uh, to be too stressful about a polynomial, because it is so easy. Okay, for a polynomial, for the critical points, you can just check the critical points when f prime is equal to 0. Okay? Okay, if you differentiate this, you will get 3x squared minus 3, and then you factorize, and then if you let this equal to 0, you can find its roots at x equal to 1 and x equal to -1. Okay, and then you can check that x equal to -1 and x equal to 1, is it a relative maximum or relative maxima based on the table. Okay, okay, for this one, this is not a polynomial, so you have to be careful with this one. For the previous one, it is a polynomial, but this one is not. Is it? If you differentiate this function f, you will get what? You will get 5x minus 2 divided by x to the power of 1 over 3. Okay, so there is 2 points that you have to consider here. So one is x equal to 2, which make f prime equal to 0, and another one is the point x for which f prime is not defined. What make f prime fail to be defined? It is when the denominator is equal to 0. That is x 1/3, 1 over 3, x to the power of 1 over 3 is equal to 0. Okay, so this is when the denominator is equal to 0. When the denominator of f prime equal to 0, then f prime is not defined. Okay, so there is two critical points for this function here. One is x equal to 0, that is for when f prime equal to 0, and then another one is when the denominator of f prime is equal to 0, that is x equal to 0. Okay, so there is 2 points. Okay, so this is the graph for the function. If you look at the graph, there's one stationary point as expected, which is at x equal to 2. Okay, and another critical point is at the corner point. So this is a corner point. Even though if you check with the table, it might give you it might it's also sorry, this is also a local. It's still a local maximum. So this is also a local maximum, because amongst its neighborhood is still the maximum. So it's also local maximum. You can still say that this is local maximum, and this is a local minimum, or relative minimum. Okay, and then we go to the first derivative test. So this is like what we have done before by using table. Okay. For the critical points, when it is a stationary points, stationary points means f prime is equal to 0. Okay, so this is a critical points, obviously it's a stationary points because f prime is equal to 0 over here, and then it's a relative maximum as well. Okay, if you look at this graph here, this is a critical point and it's a corner point, not a stationary point. Why is that? Because f prime is not equal to 0 over here or at this point. Okay, it happens because f prime failed to be defined. Okay, this is happens because f prime not defined. F prime is not defined here. It's not a stationary point because f prime is not 0 and it's a relative maximum. This is still a relative maximum because amongst its neighborhood is still the maximum. Okay, this is a critical point, means that f prime is equal to 0 for this point. It's a stationary point. Okay, critical points. Yeah, and then it's a stationary points because of this one, and obviously it's a relative minimum. Okay, this is a critical points, not a stationary points, because f prime is not equal to 0. This is a corner point like this one. For this point here, f prime not defined. Okay, and obviously it's a relative minimum. Okay, and then here is a critical point. Okay, if you check the behavior by using the table, it will be increasing and increasing again. So obviously it is not a maximum or minimum points. Okay, so it's critical points because f prime is also equal to 0. Over here is a stationary points because of that. Okay, f prime equal to 0 is inflection points because from the behavior is increasing and then increasing. Okay, it's increasing and increasing. It's always increasing, and it's not a relative extrema. This is called inflection point. This is inflection point as well. If you check the table, it will be decreasing and then decreasing again. Okay, it's a stationary points because f prime is equal to 0, inflection points. Okay, and then not a relative extremum, not a relative maximum or not a relative minimum. Okay, extremum means either minimum or maximum. And then for this one, it's inflection points, but different way of inflection point. For this one, this is a stationary points because f prime is equal to 0. But is this for this point here, f prime is not equal to 0. F prime is not equal to 0. Okay, so that's why it's not a stationary point. Okay, this is a stationary point because f prime is equal to 0 over here. F prime equal to 0. But for this one, f prime is not equal to 0. But it's also inflection points because it's increasing and then increasing. Right? It's a critical points. Okay. Critical points. What happened to the value of f prime? F prime is not defined here. F prime not defined. for this point because it has a vertical tangent. This is vertical tangent. Okay, it's also for this graph. It's not a stationary point. It's still an inflection point and not a relative extrema. Okay, so that's it. Okay, now let's look at example 4. Y equal to 3x to the power of 5 over 3 minus 15x to the power of 2 divided by 3 as a critical points at x equal to 0 and x equal to 2. Okay, we have showed this one. It suggests that f has a relative maximum at x equal to 0, okay, and relative minimum. Confirm this by using first derivative test. Okay, so you already know this. So f prime is equal to 5x minus 2 divided by x to the power of 1 over 3. So this is the f prime. If we let this equal to 0, to find its critical points, first you let it you let f prime equal to 0. So the x is equal to 2. And then you know that this function f prime is not defined at x equal to 0 because the denominator is equal to 0 when x is equal to 0, right? So x is equal to 0 is also the critical point. So this is one critical point and this is another one. Okay, now we divide the real line system with respect to these two critical points. So one is x is greater than negative infinity up to 0, okay, because we have this critical point x equal to 0 here. And then the second interval will be from 0 up to 2, okay. And then the third one will be from 2 up to infinity. So we have these three intervals, okay. So so for the behavior, then we check the sign of f prime. Okay, can you please check for me? Is it positive? Is it negative?
Positive, negative, positive.
Okay, positive, negative, positive. So it means that for the behavior, okay, behavior of f, okay, so this is increasing, this is decreasing, and this is increasing again. Okay. So the point x equal to 0, for x equal to 0, it's increasing and then decreasing. So x equal to 0 might be the will be the maximum point. Okay, will be the relative maximum point, and x is equal to 2 will be the relative minimum point. Okay, is it okay? Okay, good. Okay, so this is the conclusion from the first derivative test. Suggests that f has a relative maximum at x equal to 0 and relative minimum at x equal to 2. Confirm this by using first derivative test. So it's confirmed. Okay, we have done that. Okay, and then for the second derivative test, the second derivative test is always about concavity. When we say about concavity, normally it's also deal with the inflection points, right? So if this is concave down, this one is concaving up. There must be one point here, one point in between these two, relative maximum and relative minimum, which will be the separator between concaving down and concaving up. And this point here is called inflection. If you check with the first derivative test, this point here, the interval before it will give you decreasing, and it will be decreasing again, or it will be increasing or increasing again. So it means that the behavior doesn't change before and after the points. Okay, so that's why it's called inflection points. But somehow we have to note that the concavity will change. It will be concave down and after that concave up, or concave up and after that concave down, like this. Okay, so there's a point in between these 2 points which will be the inflection point. Okay, okay, for the second derivative test, it means that we have to differentiate twice. First derivative, we just have to differentiate only once. Okay, now let's look at the example for the first derivative. Sorry, for the second. Find the relative extrema. Find the relative extrema of y equal to 3x to the power of 5 minus 5x to the power of 3. Okay, so the y or the f here is 3x to the power of 5 minus 5x to the power of 3. Okay. And then normally first thing that we have to do is to use first derivative test before we go to the second derivative test. Okay, this is just a polynomial, so we might we won't have problem with the corner points because it's always continuous. There is no corner points, there is no vertical tangents, so the critical points will be from f prime equal to 0. Okay, so the critical points will only obtain from this f prime equal to 0. It won't be from the denominator of f prime equal to 0. Okay, you don't have to be careful about that. Okay, so if you differentiate f prime, you will get 15x to the power of 4 minus 15x squared. Okay, you factorize this, you get 15x squared and then x squared minus 1. You let this equal to 0, right? And after that, you get x equal to 0 and x equal to negative 1 and x equal to 1. So you have 3 various points. Okay, so from these 3 various points, you decide the interval. Okay, x is less than negative infinity up to -1, right? And then -1 up to 0, okay? And after that, 0 up to 1, and x equal to 1, x from 1 up to infinity. So these are the 4 intervals that you have. Okay. And then we check for the sign. The sign of f prime. Can you please check for me?
Positive, negative, negative, positive.
Positive,
Negative, negative, positive.
okay. So this is increasing, decreasing, and then decreasing, and then increasing. Okay. So from this, what can you decide? So for x equal to -1, it is increasing and then decreasing, right? Increasing, so this is maximum, local maximum or relative maximum. For x equal to 0, it's decreasing and then decreasing, right? So it's like we cannot say that it is either relative maximum or relative minimum. Okay, so x equal to 0 might be inflection points. And then obviously for x equal to 1, we have what? We have decreasing and then increasing. So this one is a minimum. This is a minimum, relative minimum. So x equal to 0 is inconclusive for the first derivative test. It's inconclusive, okay? It's inconclusive by using inconclusive for the second derivative test. So we have to use first derivative test. Okay, so if you use first derivative test, then it's fine. It's already fine. Okay, because we know that it's decreasing and then decreasing. Obviously, x equal to 0 is the inflection point. But if you use the second derivative test straight away without using the first derivative test, then you might have problem. My suggestion is you use both to confirm. Okay, you just apply both tests, so you can confirm that you have the solid validations, whether it is inflection points or maximum points or minimum points. Okay, so if you differentiate f double prime, you will get what? From here you will get 50 multiplied with 4. Berapa?
60.
60. So
60x power 3.
60 adds to the
Yes.
power of 3 minus
30x. 30x.
30x. Okay, so 30x. And then you factorize, you get 30x, and then 2x squared minus 1. Okay, you equate this equal to 0. Okay, you will get what? You will get x equal to 0, and then you get what? This one you will get 2x squared equal to 1. Is it? Okay, and then x squared equal to 1/2, right? It means your x will be plus minus square root of 1/2. Okay, Wait, I try to read this one. Why it doesn't say 330x? Okay, so this is okay. For the second derivative test, it's not that we have to equate f double prime equal to 0, but if we use the same critical points as we get from f prime equal to 0, so we don't need to factorize. We don't need to do this step. For the second derivative test, we have to use f prime equal to 0, so we don't need this step. Okay, we don't need this step. We don't need to equate it equal to 0, because the critical points that we're gonna use will be the same. Will be the same from the first derivative test for f prime equal to 0. So x equal to -1, x equal to 0, and x equal to 1. Okay. So this is not needed. This part is not needed here. Okay. And then what? And then for x equal to -1, we have x equal to 0 and x equal to 1. For the second derivative test, you don't have to write in terms of interval. For the first derivative test, yes, the table should be the interval, because you want to find the behavior for the interval before the points and after the points, so that you can see the behavior, is it decreasing or increasing. If you test for f prime at the critical points and not the intervals, obviously you will get f prime equal to 0, because f prime for each of these points will be 0, right? Isn't it? Okay, so that's why you check for the interval. Okay, for the stationary points, for the second derivative test, yes, we use the stationary points. And then you check for the sign. You can skip this part. This is just the same. Okay, f double prime. So this is the sign. The sign of f double prime. Okay, for the f double prime, here it is negative. This is 0 and this is positive, right? So from here, if it is negative, then it's concave down. If it is positive, then it's concave up. So for these 2 points, there's no problem. There's no problem for these 2 points, x equal to -1 and x equal to 1, because we can make the conclusions. But for x equal to 0, f double prime is 0. So it's inconclusive. Okay? So we cannot determine whether it has inflection points or whether it is a maximum points or minimum points. Okay, if it is negative, then we know it is concave down, so it means that it will be a maximum. Here will be maximum, so this is maximum. If it is positive, it's concave up. Concave up means that it is a minimum, right? And then so this is for the positive and this is for the negative. Okay, for 0 it's inconclusive, you have to proceed with the first derivative test. So for this example, they use the second derivative test first before they go to the first derivative. They go to the first derivative because at x equal to 0 it is inconclusive. Okay, but normally if I were you, I will use first derivative test and then I can confirm with the second derivative test to check the concavity as well. Okay, so that's it. I think that's it. Okay, and then so that's settled for the easy functions. Now we go to the more complicated functions. Before that, let's have like 5 minutes break. Okay, 5 minutes break. Okay, so let's continue. Okay. The purpose of finding this maximum or minimum and then inflection points as well as the behavior of f is because we want to draw the graph of f. We want to draw the graph of f without having to plot the graph at each of the points. Okay. So it helps us to predict the behavior of f, okay, without having to plot the graph of f. And then there's some guidelines in order to draw the graph of f. It's not only that we know the relative extrema like in the previous subsections or sections, okay, or the concavity of f, but as well as we might want to check its symmetries, the x-intercept, the asymptotes, okay, and then the behavior of as x tends to infinity or x tends to negative infinity. Okay, in the previous sections we learned about concavity, we learned about relative extrema, we learned about intervals of increase and decrease. Then that's it, as well as inflection points. But it doesn't only stop up to these uh four properties, but we can also check for its symmetry, x-intercept, the y-intercept, the endpoints behavior, and then asymptotes, the periodicity, and uh, and what else? I think that's it. Okay. Okay. Now, let's look at the example. Okay. For the example, the graph, the function is y equal to 2x squared minus 8 divided by x squared minus 16. Okay, so this is a much complicated function compared to the previous example because this is not a polynomial. Okay, this is not a polynomial. It consists of a rational function. This is a rational function. It consists of denominator as well as numerator. Okay, when I say denominator, it means that it will have vertical asymptotes. Okay, so vertical asymptotes will happen when the denominator is equal to 0. Okay, so you have 2x squared minus 8. 2x squared minus 8 divided by x squared minus 16. Okay, so uh this is the function. Okay. Okay, so from the properties or the properties of the graph, we might want to check that the graph is symmetry. Is it symmetry or not? What is the x-intercept, the y-intercept, the asymptotes, the end behavior, and then uh, the first and the second derivative to find the relative extrema and the concavity. Okay. Okay. Let's first focus on the x-intercept as well as the y-intercept and the symmetry. Okay. Okay, for the x-intercept. X-intercept is when y equal to 0. What is the point for the x-intercept? Can you please check for me? y is equal to 0. Y equal to 0, it means that you will have 2x squared equal to 8, right? So x squared equal to 4, it gives you x equal to -2 and x equal to 2, right? And then for the y-intercept, x is equal to 0. If you let x equal to 0, you will have y equal to 1 half. 1 half, isn't it? 0, 0, this is -16, so 1 half. So y will be 1 half. So 1 half will be the y-intercept. Okay. And then we want to check whether this is a symmetric function or not. Okay. Is it symmetric about y-axis? Is it symmetric? Okay, how do we check? You can choose, let's say, 2 points. Okay. Can we check for x equal to 1 and x equal to -1? Does this give you the same y? If does, then you might want to check for x equal to 2 and x equal to -2 to confirm. Take several. Okay? Take several points. What will be the point of y? If it does not give you the same values, then you automatically says that it is not symmetric. What about the value for both of the points? The value of y for both of the points. Is it the same? Are they the same or not?
No.
The same, doctor.
For x equal to 2 and -2, are they the same?
Yes.
Yes. So both of them, for all these points here, is somehow illustrate that y is symmetry. If you are not confirmed with this, you can check with several other points. So let's say x equal to 3 and x equal to -3 and check. Okay. If it still gives you the same, then you can say that the graph fx is symmetry. Symmetry about y-axis. Okay. It's symmetry about y-axis, right? Okay. And then okay, we have done that. We have done the x-intercept. We have done the y-intercept. Okay, now let's go to the asymptotes. Okay. Okay, asymptotes. So this for this function here, we have to be careful, as I mentioned before, because it is a rational function. You will have a vertical asymptote. Vertical asymptotes Okay, when the denominator of f is equal to 0. Okay, so we have to check for the vertical asymptotes. Okay, for this one, the denominator is x squared minus 16. So denominator is x squared minus 16. You let this equal to 0, it gives you x squared equal to 16. It means that the vertical asymptote is at x equal to 4 and negative 4. That's 2 points. There's 2 points for the vertical asymptotes. Okay, is it okay? Okay, now we go to the horizontal asymptotes. Horizontal asymptotes normally deals with the limit. Limits are the endpoints behavior. Endpoints behavior. Okay. Limit as x tends to negative infinity or x tends to positive infinity. So this is the things that we have to look at. Okay, so for this one, let's check for the functions endpoints behavior. So 2x minus 8. So fx is equal to 2x minus 8 divided by x squared minus 16. Okay, so for the limit x tends to plus infinity, okay, for fx, okay, it will be what? It will be infinity divided by infinity, right? So you use L'Hopital rule, isn't it? So it will be the limit x tends to plus infinity. You differentiate the numerator, it gives you 2. You differentiate the denominator, it will give you 2x. Okay, and then, is this correct? 2x squared. This is not 2x, it's 2x squared. And this is 2x squared. So for this one, you differentiate, you will get 4x. Okay, so for this one, if you substitute x equal to infinity, it will be infinity over infinity, or you can just cancel out the x, right? It will give you 2. If you still want to apply the L'Hopital rule, you differentiate the denominator, you will get 4. Sorry, numerator you get 4, and denominator you will get 2. So it's fine. So it will give you what? It will give you 2. Okay, so the limit of f as x tends to infinity is equal to 2. Okay, and then what about the limit of f as x tends to negative infinity? I think it's just the same. Yeah, it will be the same. It will also give you 2. Okay, so these 2 points, these points here, x equal to 2, will be the horizontal asymptote. Okay. Okay, what's next? We check with the first derivative test. Okay, now let's go to the first derivative test. First derivative test, we have to differentiate. It's not easy for us to differentiate, right? You have to apply quotient rule, isn't it? But it is doable. Okay, but we skip that part and cheat a bit and find its y prime. So this is the y prime. So this is the y prime. Okay, from here, you let y prime equal to 0 and find the denominator equal to 0 to find its critical points. So the critical points is when f prime is equal to 0, f prime is equal to 0, or the denominator of f prime is equal to 0, right? Because f prime is failed to be defined. Okay, at the critical points, isn't it? So for f prime equal to 0, the x will be 0, isn't it? So for this one, x is equal to 0. And then for the denominator, sorry, this is f prime. The denominator of f prime equal to 0, x squared is equal to 16. So x will be plus minus 4. Okay. So we have how many intervals here? We have how many critical points? 0, 4, and negative 4. Okay, but it doesn't stop there. We still have to consider the horizontal asymptote as well. In getting the intervals, we still have to consider not only its critical points, but also its horizontal asymptotes. Okay, for complicated functions, not simple polynomial functions. Okay, before this, from the previous example, I showed you that the intervals are normally obtained just from the critical points. But now we have to consider not only the critical points, but also the horizontal asymptotes as well. Okay, so from the critical points, we know that the function has three critical points, uh, that are x equal to 0, x equal to 4, and x equal to negative 4. Okay, so from here, we decide the interval. So x is from negative infinity up to negative 4. Okay, and then negative 4 up to the critical points. Sorry. Negative 2. Why is it negative 2? Why is it? Wait, the set second x. So it's the vertical asymptotes. Okay, this is correct. The set of points vertical asymptotes. Vertical asymptotes. Ah, okay. The critical points. We still do not find the critical points, right? Have we done that? No, not yet. Okay. Okay, erase this one first. Now, sorry. We have done that. We find it from here. Plus minus 4. So, vertical asymptotes. Vertical asymptotes is at plus minus 4. Plus minus 4. Critical points 0 plus minus 4. Okay. And then we have vertical asymptotes. Wait, I still don't see why we have to consider negative 2 here. But when determining the intervals, why do we have to consider negative 2? Negative 4 is correct. They should also consider 0, but they don't. F prime is equal to 0, satisfied that F prime equal to 0, isn't it? So they should also consider F prime. They should also consider x equal to 0. So these three values, x equal to 0, x equal to 4, and x equal to negative 4 is correct. But there is no x equal to 0. Something that we have to look at. They should also consider that. Okay. They should not neglect x equal to 0 here. Okay. They should consider x equal to 0. And then x equal to 2. I think let's try to do it our way, okay, instead of their way, because they use different table. Somehow here it has test point, this is value of y, and this is sine of y. It's not something that we always done. Okay. Okay. Let's just consider the intervals. Negative infinity up to negative 4, and then negative 4 up to 0. Okay. And then what? And then 0 up to 4, and then 4 up to infinity. Okay, so this is our first derivative test. We don't have to follow the way the authors of the book write. We do our normal first derivative test. Okay, so for this one, this is the sign of f prime, and this is the behavior of f. Can you please check for me? Is it positive or negative? Or the first one?
Positive, positive, negative, negative.
Positive, positive, negative, negative. So this is increasing, increasing, decreasing, decreasing. Okay. This is from the first derivative test. Okay, what about the second derivative test? So for the second derivative test, the second derivative is this one. Okay. We use the same critical points. Okay. So x equal to -4, x equal to 0, x equal to 4. Okay, and check the sign of f double prime. Okay. Can you please check for me? Is it positive or negative?
Positive, negative, positive, Doctor.
Positive, negative, positive. So it means that this is concave up, concave down, and this is concave up. This is concavity. Okay. So, okay, let's draw. Let's draw the graph. Okay. So we know that the graph is symmetry. Okay. And then let's plot several points. So -4, and then you have -2 as well. And here is +2, and this is 4. Okay. And obviously you have 0. Okay, now the x-intercept x equal to -2, 2, and 0. Okay, x-intercept this point here, this point, and this point. Okay, and then you have what? You have y-intercept at y equal to 1/2. Okay, y-intercept y equal to 1/2. So what about this point here? X equal to 0. Does it also... Sorry, can we check again? x-intercept. X-intercept is only -2 and 2, not x equal to 0. So this is wrong. So this is correct. This point is correct, but this is wrong. Okay, let's erase this point. Okay, so we plot the points that we know. Okay, what else? We have vertical asymptotes at x equal to 4 and x equal to -4. So vertical asymptotes means that you have to draw a vertical lines. Okay, vertical lines, and here also we have a vertical lines. Okay. Okay. We have checked the endpoints behavior, right? The endpoints behavior is, it gave you y equal to 2. So y is equal to 2. So if this is 1/2, y equal to 2 might be over there. Okay, you have to draw another line here. Okay. So this is your horizontal asymptotes. Okay. Let's draw it a little bit lower. Okay. Instead of 2, here let's write 2 here. Okay, now since it has a vertical asymptote, we have to check for another limits. Okay, which is the limit of f as x tends to -4 from the left. Limit of f, this is because we want to check the behavior of the of the graph for f over here. We know that it has vertical asymptotes, but we don't know what happens to the graph around or near to this vertical asymptotes. So that's why we have to check for the limit of f as x tends to -4 from the left, limit of f as x tends to -4 from the right. Okay, limit of f as x tends to 4 from the left, and limit of f as x tends to 4 from the right. Okay, can you please check for me? For -4 from the left, you might want to take what from the left? You might want to substitute, let's say -4.0001, and see what will be the value. Is it negatively large number, or is it positively large number, or is it times to 0? Okay, can you please check for me? What will be the value?
Positive large number.
Positively large number for the first one, is it? So plus infinity. What about this one?
Yes.
What the second one? About the second one? This one? Negative 4 from the left. Sorry, from the right. You might want to choose, let's say, negative 3.999. Okay? Negative 3.99.
Negatively large number.
Negatively large number. Negative infinity. What about this one? 4 from the left and 4 from the right.
Negatively large number.
Negative infinity. And this one?
Positive infinity.
Positive infinity. Okay? So we got all these four sets. Okay? So, limit of f as x tends to negative 4 from the left is coming from here. It will go to plus infinity. And then we have a horizontal asymptote as x tends to negative infinity, the y will be 2. So it's coming from here. And then it goes up. It goes up to plus infinity as x tends to negative 4 from the left. Okay, so this will be the graph. For the second one, for this one, negative 4 from the right, it will be negative infinity. Okay, negative 4 from the right, it will be negative infinity. So it will be coming from down, from below. And then it will pass through these points. Okay, because this is our x asymptotes, and then it will goes to the y asymptotes. It will go down to the x asymptotes, and then from here it will go down to negative infinity because x tends to 4. The limit of f as x tends to 4 from the left, it will be negative infinity. So it will be like this. Okay, it will be like this. And then for this one, limit of f as x tends to 4 from the right, it will be plus infinity. Okay, it will be plus infinity. So it's coming from up, and then obviously you have horizontal asymptotes here. So this will be the shape. This will be the shape. Okay? Is it okay? Any questions? Any questions about this? Anyone? I think we get the same graph as shown. This one. It's the same one. Any questions? No? Okay, so I assume all of you can understand this. Okay. For complicated or rational functions, you have to consider the vertical asymptotes. Okay, so the vertical asymptotes is obtained when the denominator is equal to 0. Okay, and then obviously you have to check for the horizontal asymptotes as well to see the endpoints behavior. Okay. Okay, next will be what functions? This is the graph. X squared minus 1. X squared minus 1. Okay, so x squared minus 1 divided by x cubed. X squared minus 1, again, it is a rational function. x squared minus 1 divided by x cubed. So this is the y. Okay, and then okay, can you please check for the x as in y-intercept. Y-intercept is when x equal to 0. The x-intercept is when y is equal to 0. Can you please check it for me? Okay. X is equal to 0. X is equal to 0. 0 minus 1, negative 1, you divide with 0. So it will be undefined. So it will be undefined. So there is no y-intercept. No y-intercept. Okay. And then for the x-intercept, the y is equal to 0. The y is equal to 0. X squared minus 1 equal to 0. So for this one, x squared minus 1 is equal to 0. X squared is equal to 1. X will be plus minus 1. Okay. So we will have 2 x-intercept. Okay, now, does this function symmetric or not? Okay. Can you please check for x equal to negative 1, x equal to plus minus 1, what will be the y? For x equal to, let's say, negative 2, and x equal to plus 2, what will be the y? Okay, can you please check for me? Okay, is it symmetry or not?
Yes.
Not.
Hmm?
Not.
Not symmetry.
Not.
Okay, it is not symmetry. And then what else? Um, this function here will have vertical asymptotes at x cube equal to 0. Okay, so for the vertical asymptotes, x cube is equal to 0, so x is equal to 0. So it will have vertical asymptotes at x equal to 0. What about horizontal asymptotes? Horizontal asymptotes is when the limit of f(x) tends to plus infinity, as well as the limit of f as x tends to negative infinity. Okay? So x squared minus 1, so the y divided by what? X cubed. Okay. So infinity over infinity, we use L'Hopital rule. From the L'Hopital rule, it will be 2x. Okay, so this one limit 2x divide by 3x squared. Okay, Again, it will give you infinity over infinity, and then you apply L'Hopital rules again. You will get what? Limit 2 divided by 6. 6x. Okay? X tends to infinity. And then from here, it will give you what? 0, right? 2 divided by infinity, it will give you 0. Okay? 0 will be the horizontal asymptotes. What about this one? This one also give you 0. Okay? For the limit f(x) tends to infinity, negative infinity. Okay, next. Next are the critical points. Okay, the critical points. What will be the derivative? So this is the derivative. This is the derivative. The critical points is when you have x equal to negative square root of 3 and x equal to positive square root of 3. Okay, so these are the 2 points, as well as when the denominator is equal to 0, which is at x equal to 0. Okay, is it okay? Okay, so we have critical points. Critical points, x equal to negative square root of 3 plus square root of 3 and 0. Okay, and then in determining the intervals, you have to also include the points for the vertical asymptotes. Okay, the vertical asymptotes is this one. Sorry, this is the vertical asymptotes, which is at x equal to 0. Okay, so vertical asymptote is at x equal to 0, which is also its critical point. So we just have to consider these 3 points, by the way. Okay, so x negative infinity up to square root of 3, negative square root of 3, and then negative square root of 3 up to 0. Okay, and then 0 up to square root of 3, and then square root of 3 up to infinity. Okay, is it okay? Okay, so these are the intervals, and then here it will be the sign of f prime, and this one is behavior of f. Can you please check for me? Is it positive or negative for the first interval? Is it positive or negative?
Negative, positive, positive, negative.
So this is decreasing, increasing, increasing, and then decreasing. Okay. So, are we done? Okay, let's try to plot the y-intercept. No y-intercept. Okay, the graph does not have y-intercept, and then we have intersection at x equal to -1 and 1. -1 and 1. Okay. And then critical point, negative square root of 3. What will be the value? Exact value for this one in decimal places.
Negative 1.732.
Negative 1.732.
32.
Okay. So it's over here. So negative square root of 3 is over here. And this is square root of 3. Okay. What else? So this is the plot. Okay, square root of 3 is the critical points. Okay, is the critical point. The critical points. Okay, can you please check for f of square root of 3 as well as f of negative square root of 3 for me?
0.38.
0 for both. Is it for both?
0.38 and negative 0.38.
Negative 0.38. Okay. So this one is negative 0.38, and here we have 0.38. Okay. So for this one, the plot is over here, and for negative square root of 3 is over here. Okay, let's cross this point. Do we have vertical asymptotes? Yes. Yes, isn't it? Vertical asymptote is for x equal to 0. Okay, so the vertical asymptotes is at x equal to 0. Okay. This is the vertical asymptotes. Since it has a vertical asymptotes, means that we have to find the limit of f as x tends to 0 from the left, as well as the limit of f as x tends to 0 from the right. Can you please check for me? Is it positively large number or negatively large number or what? What is the answer?
Negative infinity.
This is negative infinity. What about this one?
Positive infinity.
Positive infinity. Okay. Okay, what else that we miss here? Limit f as x tends to plus infinity. So this is for horizontal asymptote. Or for the endpoints behavior. Endpoints behavior is always for the horizontal asymptotes. Okay, so we have horizontal asymptotes at x equal to 0. Okay, let's draw another line. Okay, so this is horizontal asymptotes. Okay, now as x tends to 0 from the left, it's coming from the negative infinity. It's coming from we have horizontal asymptotes at x equal to 0. So it means that for the endpoints behavior, it should comes from here, doesn't it? It's coming from here, from negative infinity. And then we know that the limit f as x tends to 0, from the left it is negative infinity. Is this correct? It doesn't seem like that from the graph. Can you please check it again? It seems wrong here. Can you please check the sign for me? I don't think it is correct. 0 negative and this is 0 positive. From the graph that I observed, it should be plus infinity and negative infinity.
Yes, that's right. Positive infinity.
So this is wrong.
And negative. Ah, this is
Okay, this one is wrong. These two wrong, so we have this one. So we know that it will intersect over here, which is at x equal to -1. It's coming from here. The endpoints will coming from here. So it must be below this y-axis. It's coming from this negative infinity, okay, and then it will intersect over here, x equal to -1. Okay, so this is the x-intercept, and then it will goes up because of this value, limit of f as x tends to 0 from the left is plus infinity. It goes up to this vertical asymptotes. Okay, so this is the graph. Okay, the next one, 0 positive is negative infinity. So it's coming from below. It should be coming from below. Okay, negative infinity for here. So it's coming from below, and then it will intersect at x equal to 1. Okay, and then we should have horizontal asymptotes as well at x equals at as x tends to infinity, the y will tends to 0, isn't it? So the graph will look something like that. Can we check for this one? For square root of 3, what is the square root of 3? Square root of 3 is the critical points. Critical points means that it is a stationary point. So we will have a minimum. So here there will be a minimum before it goes up. So this one will be relative minimum, and this one, it will reach its maximum over here. Okay, the graph will be like that. Okay, because this is a critical point. This is critical points. Critical points means it is a stationary point. It could be either minimum points or maximum points. Okay, so if you look at the graph, yes, it reached its square root of 3 is somewhere here, 1.7 something. So it reached its maximum here, and then it reached its minimum over here. Okay, is it okay? What about this point? Between 2 and 3, what is this point? I think this is inflection point. You can check the inflection point. And this one is inflection point as well. We don't check for inflection points, but if you want to check for the inflection points, you can check for f double prime equal to 0. Okay, you can check for f double prime equal to 0. You can check it at home after this. So somehow this is the graph that we have seen. Okay, I hope it is clear. Okay, any questions? Anyone? Is it okay? Because you will have to attend your test on, I think you will have a quiz tonight, isn't it? If I'm not mistaken, you will have a quiz.
Yes.
And
Yes,
then for
doctor.
next week, there will be a test, which also cover this part here, derivative and application of the derivative. Okay. I think that's it. Okay. Others, you can try to do it as exercise. Okay. Absolute extrema. Absolute extrema is the global one. Okay. I normally use local minimum or local extrema instead of relative extrema. And for the absolute, I normally use global, but they are actually the same. Globals or absolute means that the highest one. Okay. The absolute maximum means that the highest value for the maximum values. Okay, and then if you have absolute minimum, means that the lowest value for the points along the graph. Okay, so for example 1, find the absolute maximum and minimum of the functions on the interval 1, 5. 1, 5. So this is interval from 1 up to 5. If you have square brackets, means that it also includes the point 5 and 1. If you have smile bracket like this one, smile, 5, then it doesn't include this point 1 and it doesn't include 5. If it does include 5 and 1, means we have to write the square bracket instead of smile bracket. Okay, find the absolute maximum. If it also includes the endpoints like this one, means that we have to check the value of f at the endpoints like this one. Instead of just checking for the stationary points is when f prime f prime is equal to 0, okay, for the stationary points. We have to check for the endpoints as well. Okay, so that's why for the stationary points, you have f prime equal to 0. You factorize somehow, you get x equal to 2 and x equal to 3. Okay, so there's 2 stationary points, 2 and 3. And then you will have endpoints, which is at 1 and 5. Okay, so you find f1, f of 2, f of 3, and f of 5. And then you compare. Amongst all this value, what is the value that gives you the highest one? Okay, the highest one will be 55. 55 means that this is the absolute maximum, and the lowest one is this one. So this is the absolute minimum. Okay, is it okay? Is it okay? Any questions? Anyone? No? Okay, good. Okay, now let's look at example 2. For the example 2, this is f prime is this one. It is in terms of rational. So the critical points will be at x equal to 1 over 8 as well as at equal to 0, which is when the denominator is equal to 0. So these are the two critical points. And then we also consider the endpoints because these intervals is involving the square bracket. So -1 and 1. This point here, -1 and 1, also includes in this for this interval. So -1 and 1, the endpoints we have for the endpoints, and then you check for f of x at all these points. Okay, you check if we check the absolute maximum, will be this one, and the absolute minimum will be this one. Okay, yeah, that's it. Okay, now let's continue with example 3. Example 3, they consider the whole interval from -infinity up to +infinity. So for this case, you don't have to find the f of the endpoints. Okay. So let's consider this one. Okay. Determine by whether this function has, okay, if it doesn't state the interval, it means that they consider the whole interval from negative infinity up to infinity. So 3x to the power of 4 plus 4x to the power of 3. If you differentiate, you get this. You equate it equal to 0. So your critical points will be x equal to 0 and x equal to negative 1. Okay? There's no endpoints that you have to consider. It's from negative infinity up to infinity. So that's the only points that you should check is f of, in this case it is p. So p of 0 and p of negative 1. So p of 0 is 0 and p of negative 1 is equal to negative 1. Okay? But then you have to check the endpoint's behavior as x tends to negative infinity and as x tends to plus infinity. So the limit of p as x tends to negative infinity, if you substitute it here, it will give you what? It will give you plus infinity. It will give you plus infinity. And the limit as x tends to positive infinity for p, it will also give you plus infinity. Both will goes up from both sides, from negative side and from the positive side. I mean, for as x tends to negative infinity and x tends to positive infinity, both will give you plus infinity. Okay, so there's no way that we will have a point along this graph P which will be lower than this point. Okay, P of negative 1. Okay, so this one will be the minimum values, will be the absolute minimum. I cannot write it. Okay, and then for the absolute maximum, this one cannot be the absolute maximum. Why is that? Because the graph, we know that it will tends to plus infinity for the endpoint behavior. Okay. Okay, so there is no absolute maximum. This is not the absolute maximum. Okay, this is the absolute minimum. Okay, I think that's it. That's it for the example 4. For the example 5, determine whether the function has absolute extrema. So this example, I cannot write it on the on the it's okay. Okay, for this one, they decide the interval 0, 1, but this is open bracket, small bracket. So 0 and 1 does not include in the intervals. Okay, So we check for the critical points. So from the critical points, it is x equal to 1/2. Okay, x is equal to 1/2. F of 1/2 is -4. And then we check for the n. Since it is restricted from 0 up to 1, it means that we check for the limit as x tends to 0 from the right hand side and x tends to 1 from the left hand side only. Okay, because it's restricted from 0 up to 1. We just want to consider within this interval. So x tends to 0 from the right and x tends to 1 from the left. So we find these two limits and get negative infinity, both of them. Okay, so x equal to 1/2 will be the absolute maximum, but there will be no absolute absolute minimum. There is no absolute minimum because it's going down. We know that it's going down. Okay, the absolute maximum is at x equal to 1/2. Okay, this is the application. It might also be asked in the test. So I suggest for you to read this part here. I mean these sections. It's not difficult. You just have to apply the critical points. So let's say we look at example 2. For the dimensions, we have V equal to this one. V is volume. Okay, so from the cardboard or from the box, we know that the volume is given by this one. This is the equation for the volume. And then the problem asks us to get the largest volume. The size would be the square. So it means that the questions ask us to find the x. Okay. Okay, so obviously you have to differentiate to get the critical points. Differentiate V. Okay, you got this one. The critical points will give you x equal to 10/3 and x equal to 12. Okay, but then x equal to 12 x equal to 12 falls outside the interval 0, 8. Okay, why is that? Because if the length of this is 16, it means that the x will be here, and this one, the most possible the maximum values for x that it can reach is only 8, because 16 divided by 2. Okay, so for x equal to 12, it's outside the interval 0, 8. 16 divided by 2, it gives you 8. Okay, so the only critical points that we want to consider is x equal to 10 divided by 3. Okay, and then you can substitute this and get the answer. Okay, at x equal to 10/3, the V will be 7 to 6. Okay, that is your maximum volume. Okay, that will give you the maximum values. Okay, I think you can try to read all this and try to solve it. They are just the applications. It means that you just have to differentiate, find the critical points and something like that. Okay, I think you can try to do it at home. Yeah, I think we finished. Is it? Yeah, we finished. We finished this chapter. Newton's method is won't be asked. Derivative and application only. Derivative and its application for the test. For the quiz, it will be something related to the graphing. Yeah. Thank you very much. See you next week. Sorry, see you tonight for the quiz. Okay, and then I'll see you again. 12th of December will be on Saturday, I think. Let me check. Yeah, 12th of December will be on Saturday, and the time will be 8 to 9:30. Okay, for the test, 8 to 9:30 a.m. a.m. So our class, yeah, let's just cancel next week's class. Okay, thank you very much. I will post again the time to the WhatsApp group. Okay, but I hope Dr. Fauzi already notify you about the duration and time and all. By the way, if I'm not mistaken, Dr. Fauzi did post the instruction for the assignment 2. Just ignore it because we have done that. Okay, they are just almost the same with what I've already instruct you. Okay, is it clear? Okay, for the assignment 2, the video presentation. Sorry, yeah, the video assignments. Okay, just ignore the instruction given by Dr. Fauzi. Okay. Okay, thank you very much. That's it.
Doktor,
Let's just end our
Doktor.
yes.
Yang untuk next week tu, Dr. Fauzi ada out kat My Guru kata malam, Doktor.
Malam apa?
8 malam hingga 9:30 malam. Dia kata tulis PM, Doktor.
Sorry, can you please say it again because it's not clear.
Dr. Fauzi kata in My Guru dia kata 8 PM.
For which one? Is it for quiz or for test?
For test. 12 bulan.
8 to 9 on Saturday.
9.
On Saturday.
Yes.
12th of
12 bulan 12.
12th of December. Okay, just follow the instruction because he will conduct your test. Okay.
Okay, thank you,
What
Doktor.
about for quiz? Quiz should be tonight. Is it already given in the instruction in My Guru?
No, Doctor.
Huh?
Cik, Amira tengah buka tu video korang tak
For the
buku.
quiz, Dr. Fauzi already share the time for the quiz or not?
Already shared.
Okay, is it tonight?
Yes.
Yes.
Yeah.
Yes,
Okay.
tonight.
8 ah? 8.
Yeah, 8 until 8:30.
Okay. So thank you very much. Okay.
Right.
Good luck.
Okay, Doctor.
That's it. I will end the recording.